Okay, we're going to continue our discussion of circular motion today, as you can probably tell from the title here. Again, my lapel mic is broke, so I'm still cashing it up with this, with the microphone in my headphones, which is why I look a little funny today. So last time we talked about this situation, which is that if you have some sort of air hockey table, and if the student center was open right now, we talk about the air hockey table there, but if you had a string in the middle of the table and tied it to one of the hockey pucks, it would sort of swing around and do something like this. So you can see the velocity vector there is sort of always perpendicular to the path, and then there's a force vector towards the center because there's a piece of string, and that string is exerting a force. Whenever a string exerts a force, we call that force a tension, and so that makes it move in a circle. The acceleration is always in the same direction as the force if there's only one force, so the acceleration is towards the center of the circle if the thing is moving in a circle. Last time we talked about how when a thing is moving in a circle, the acceleration is v squared over r, and I had this sort of explanation where this equation comes from, which I don't want to go over now. This is sometimes called the centripetal acceleration, but for all intents and purposes, it's just the acceleration of when a thing is moving in a circle. So now let's talk about some new stuff. And a lot of the new stuff we're going to talk about today has to do with quantifying how fast or how slow something is spinning. So, for example, the Earth spins every 24 hours. And if you ask me, that is a little bit on the slow side, right? It takes 24 hours for it to spin all the way back to where it was. But on the other hand, this implies that the surface of the Earth is moving at something like 1,000 miles an hour. And so we need some sort of language for talking about how fast things are moving and rotating and stuff like that, as it applies to circular motion. So how did I know that the surface of the Earth is moving at 1,000 miles per hour? Well, I Googled it, like everyone else. I can Google it, but how did I know that Google is right? Well, consider the following. So the period of the motion, in other words, the period is the time it takes for the thing to get back to where it was, is capital T. And so for us, that's 24 hours. We want to convert that into seconds. So in this course, we're going to give this capital T for the period. And the speed at the edge of the thing that's moving is the distance that's involved in that rotation divided by the amount of time it takes for it to make that rotation. So this would be the circumference of that circle is 2 pi r, and then the time was just the period of the rotation, so that's 24 hours. So we get something like this for the speed of the surface of the Earth as it's rotating. So we can convert this to meters per second. So the radius of the Earth turns out to be about 6,000 kilometers. 24 hours, well, there's 60 minutes in each hour, there's 60 seconds in each minute. And so we can run the numbers on this and conclude that this is almost 500 meters per second. And then once we have that, we can convert that into miles per hour. So that's how I knew that Google was right about what the speed at the surface of the Earth was. Now, sometimes instead of the period, it makes sense to write down and talk about the frequency of something, the frequency of the motion. So something that may take a very short amount of time to do a full cycle, it may make more sense to talk about the frequency than is the period, although the two are closely related to each other, right? So if the period is the number of seconds that it takes to make one cycle, the frequency is the number of cycles per second, right? Because 1 over the number of seconds per cycle is the number of cycles per second. So typically the frequency is in terms of, just a second for me. So typically the frequency is in terms of the number of cycles per second, so we can write that down as inverse seconds, for example. We can also talk about equivalent to that is hertz. So cycles per second is also called hertz. This is named after a German physicist that helped to develop, invent radio waves, first radio transmitter. So, for example, I don't know if there's any musicians in the class, but an A note, is 440 cycles per second, and the thing that is cycling is the density in the air. So the density of the air is fluctuating, and the number of cycles that it fluctuates is 440 times a second. So this is what 440 times a second sounds like, kind of like that. And so higher pitches would be more than that, lower pitches would be less than that. But that's the basic idea. Now, in other applications, so talking about engines or motors or things like that, we're often going to talk about rotations per minute. So whereas frequency is cycles per second, sometimes people will talk more about rotations per minute. So this is, I forget what this is called on a car, whether it's an odometer, tachometer, or whatever it is. But this is telling you something about the, see that there's an R divided by min, so this is, it's telling us that it's something like, it's almost 8,000 rotations per minute, so it's about 8,000 RPM is what this meter is telling us right now. So if you have frequency, how do you figure out RPM? If you have RPM, how do you figure out frequency? Well, RPM is the rotations per minute, and there's 60 seconds in every minute, so if we take the number of cycles per second and multiply by 60, that will give you the rotations per minute. And if you have RPM trying to figure out frequency, you can do vice versa, divide by 60. So it's pretty easy, but people find ways to trip it up, and when you're doing a midterm or something, there's ways to fumble this pass, but it's not any more complicated than that. Now, another way of quantifying the rate at which something is spinning is referred to as the angular frequency. And so instead of the cycles per second, it's really has to do with how much angle have we swept out in a second, and specifically an angle in radians. So really, this is radians per second. So this is the change in angle over the change in time that gives you a radians per second. Now, in principle, we could do this as degrees per second, but we tend to define this in terms of radians per second. And so because of this, this symbol, by the way, this is the symbol omega. It's a Greek symbol, omega. Everybody wants to call it W, and I agree, it does look like a W, but technically it's the Greek symbol omega. And so because it's radians per second, and we're talking about cycles, every circle has a total of 2 pi radians for that circle. And so to go from cycles per second to radians per second, you just multiply by 2 pi. Okay? And there will be problems in which I might give you the frequency, and what you'll really need is the angular frequency. Sometimes this is called the angular speed. I think the angular frequency and the angular speed are about the same thing, if you ask me. So sometimes they'll give you frequency, what you really need is the angular frequency. Sometimes they'll give you the period, and what you really need is one of these two things. So just be ready to convert from one to the other if needed. Now, an interesting thing is that, and the reason that people like this symbol so much, is that if you look at what it does to some of the equations, so for example, velocity equals 2 pi r over t, we talked about this one earlier. Well, 1 over t is the frequency, and then 2 pi times the frequency is omega, and so this thing turns into r omega. Technically, that's an equal sign there. So arguably, this is much more elegant than that. Maybe. I don't know. And then you can also rewrite this thing, so v equals r omega. So v equals r omega, you can stick that into here, you get r squared omega squared. And so the r squared cancels with the r, you end up with accelerations r omega squared. And then here's a big one, which is that often later in this course we'll have things like sine 2 pi f times the time. Well, 2 pi f is equal to the angular frequency, and so this thing turns into that, which is a little bit more elegant than it was before. So that's why we physicists, mathematician people like to write it down this way instead of that way. So the next thing is a nice video. Let me see if I can mute my microphone and get it to be picked up. See what happens.
The speed of an object in uniform circular motion depends on the rate at which it moves around the center point and its distance from that point. Although both dots are rotated through the same angle, the outer dot travels farther in the same time interval and therefore moves faster than the inner dot. The small distance, delta s, that an object moves when rotated through a small angular displacement is r times delta theta. Dividing both sides by a small time interval gives the linear speed equal to r times delta theta divided by delta t. The angular displacement divided by the time interval is called the angular speed. The angular velocity, denoted by omega, is a vector quantity. Its magnitude is given by the angular speed. The direction of the angular velocity vector is determined by the right-hand rule and is perpendicular to the plane of motion. Notice that the vector, omega, does not point in the direction of motion, but is perpendicular to the direction of motion. Reversing the direction of motion reverses the direction of the angular velocity vector, omega. Angular velocity has units of radians per second.
All right, there we go. Okay, the next few slides are based on this sort of silly demo, which has a record player that's spinning around, and we're speeding it up and slowing it down and plotting the position of either an ant or a ladybug, so you can feel free to play around with that. You can see a little bit of passive aggression towards the chemistry department from the physics department, which is not coming from me. It's coming from whoever wrote this. Anyway, the following questions are sort of loosely inspired by this, coming up in one more slide. So let's review kind of what we learned and put it all together, because there's a lot of moving parts in what we just went over. So the angular speed is omega, right, which is the change in angle over the change in time, delta theta over delta t. And so because the angle is in radians and the time is in seconds, that means the units are in radians per second. The frequency is related to omega. So in one circle there's 2 pi radians, and so if you divide omega by 2 pi, you get, instead of getting radians per second, you get cycles per second. So you get something like that. And then the frequency is 1 over the period, which means that the period is 1 over the frequency, right? So the period is the number of seconds per cycle, like how many seconds does it take to do one cycle, instead of in 1 second how many cycles happen, right? So seconds that it takes to do one cycle, so it's 1 over the frequency. And then because we know how the frequency relates to omega, that means the period is equal to 2 pi over omega, which is handy in some situations. Excuse me. All right. The velocity is the distance over time for something moving in a circle. If it's moving in a circle, then it's probably moving the circumference in that time, and it's probably moving that time in the period. And so you're dividing the circumference, which is 2 pi r, divided by the period. And so the units there are meters per second. I think we can simplify this. If you think about period as 2 pi over omega, sub that into there, you can show that the velocity is equal to r omega, which is useful in some circumstances. And then finally, the centripetal acceleration we talked about is v squared over r. We talked about that last lecture. And if you sub v equals r omega into this, you end up with that, and these are all equivalent, and the units here are meters per second squared, right? So if you think about meters per second and the quantity squared divided by meters, that's how you get it. Or you can say, well, this is per second squared here times meters. So one way or another, you end up with meters per second squared, as you would expect for the acceleration. All right, so here's the actual quizzical thing I was going to ask you. So let's say that we have this is what's called a CD. Remember when people used to use CDs and DVDs and Blu-ray discs? So whopping 700 megabytes there. 80 minutes of audio. It's amazing. So let's say you have two ants that are on this thing and it's inside of a CD player, so the thing is spinning around, right? The question is, this ant number 1 compared to ant number 2, how do the periods compare between those ants that are just sort of standing on the CD as the thing is rotating around? So is it the same? Is it a factor of 2? Is it a factor of 4? What is it? So if we were in real groups, I would assign this to you, and you would talk to your neighbors, and you'd say, "What's up, neighbors? What do you think?" So what do you think? All right. The answer is A. Okay. The reason it's A is because these ants are on the CD, and if it's going around, they're coming back to where they started at the same time, in spite of the fact that one is closer to the center of the circle than the other. So the periods are the same. The next question, compare the magnitude of the velocity. By the way, this is a $20 phrase for speed. In other words, compare the speed of ant 1 to ant 2 as it's rotating here, right? So let's think about this. Is it the same? Is it within a factor of 2 or within a factor of 4? So ask your neighbors if they existed, and they don't. The answer is that ant number 2 has to be moving twice as fast as ant number 1. And the reason for that is that the speed is the circumference divided by the period, right? So we just proved that the periods are the same, but because this radius is twice as much as that one, that means the circumference is twice as much. And so if the circumference is twice as much, 2 pi r over the period is going to be twice as much as ant number 1. Because ant number 2 has to move twice as far in one period than ant number 1 does. Therefore, the speed is twice as much. Here's a tricky one. So compare the centripetal acceleration of ant 1 to ant 2. Are they the same? Are they different? In other words, what kind of acceleration would these ants feel if they were spinning around like this? And so a question, for example, is that would this ant feel, part of navigating this question is which ant feels more acceleration, this one, the one that's further away, or the one that's closer to the center? So think about that one for a minute. Minute's up. Here's the answer. Ant number 2 is actually experiencing twice as much acceleration as ant number 1. Now this is a tricky one because the centripetal acceleration is v squared over r. And so this ant is traveling twice as fast as this ant. So v squared is, if it's twice as fast, that gives you a factor of 4. So you'd think it was an acceleration that's a factor of 4, right, because of the v squared. But remember that the distance here is twice as much. The r is twice as much. And so you get a factor of 4 from the fact that you're going twice as fast. But you're dividing by a factor of 2 because you're twice as far away. So at the end of the day, you get this ant is accelerating twice as much as this ant. Part of the answer here is that this ant number 2 has experienced more acceleration than ant number 1. And a way to think about that is that if there was an ant at the very center, would that ant feel any acceleration at all? And the answer is actually no. No, if you're at the center of the thing, and if you're at the state fair or something and some giant swirling around ride, you'd get pretty dizzy in the middle, but you wouldn't get squished around and thrown around like you would if you're towards the outside of the thing. And so you can reason that the acceleration that ant number 1 feels is less than the acceleration that ant number 2 feels. Alright, this is the last one. So compare the angular speed. For me, the angular speed is the same idea as the same angular frequency. I can't think of an important difference between those two things. But in other words, compare omega for ant 1 to ant 2. Are they within a factor of 2, a factor of 4? Are they the same? So again, talk to your neighbors. Try to chat. What do you think? The answer is that they are in fact the same. Because remember that it takes the same amount of time for the ants to go through one period. And so this is the angles, this is the radians per second for ant 1, this is radians per second for ant 2. Well, it's the same, if it takes the same amount of time for the ants to do 2 pi radians, well then clearly the angular speeds are the same. So that's just a little bit of trivia. It's good to brush up on that for midterms and other purposes. Alright. So the next part is talking about the difference between the centripetal and the centrifugal force. For me, this is not a huge, like, test you to death sort of a thing. I need to say this so that we can just move on. I don't need to say it again. But the centripetal is the actual force. The centripetal force is the actual force that it takes to pull you into a circular motion. Whereas the centrifugal force is this sort of abstract force. Some people call it a fictitious force that, as we'll see, is an artifact of the fact that you're looking at some interaction on a platform that might be rotating. So there's a nice little video on the next slide that I'll show you, but let me see if I can mute my audio.
As the turntable spins, the tension in the string supplies the centripetal force that holds the disk in uniform circular motion. Like any object in uniform circular motion, the disk is accelerating. If we mount the camera on the disk, we are in an accelerating reference frame, and the disk appears to stand still. When we break the connection, the disk is seen to accelerate outward in this frame. If we try to use Newton's second law to explain this motion, we must introduce a fictitious force to explain the observed acceleration. This is the so-called centrifugal force. In a non-accelerating frame, the disk is seen to obey Newton's first law. When the connection breaks, the disk does not accelerate, but continues to move in a straight line and at constant speed. The so-called centrifugal force is not a real force. It only appears to exist in a rotating reference frame.
Okay. Okay, another nice video is this one, which has a teacher in a merry-go-round sort of tossing a ball around. The point of this is that, there really is no forces per se acting on this ball. There's no, there's gravity that's pulling down in it, but basically there's nothing magical that's bringing the ball back around to the teacher. The reason the ball comes back around to the teacher is because the teacher is spinning around and is in a different position and can kind of catch it. I suppose there's some slight gradient probably making the ball sort of slide outwards, so maybe there is a force on the ball that way. But in any case, the weirdness of this motion is primarily from the fact that we're viewing it from a merry-go-round that's spinning around. Now, you're probably thinking at this point, like, well, when is this going to matter? Like, in my professional career, I'm not going to be doing engineering on spinning platforms more than likely, and that's true. But consider the following, which is that the Earth is a spinning frame of reference. It's a spinning object. And so, for example, hurricanes experience something like this centrifugal force, and that is why hurricanes they don't tend to follow straight lines, if you notice. They tend to follow curved trajectories, and part of that is because of the wind and the Gulf Stream and stuff like that. But part of that curvature, and so, for example, The Atlantic hurricanes, they start close to the equator and they sort of curve upwards. Only part of that is because of the wind currents. A lot of that is because of the fact that the Earth itself is spinning, and that because we're spinning, that kind of leaves behind the hurricane in a certain sense. So from our perspective, it looks like it's on a curved trajectory. So if you end up in your life living on either the Gulf Coast or the Atlantic Coast, this will become very practical information for you. Otherwise, I'm sure there's a few other applications of this, but that's the main one that I can think of right now. I tend to think of that one because I grew up near Tampa, Florida, and I remember Hurricane Andrew. I remember tropical storms going over. My parents were in Florida for Irma. I wasn't, thankfully, but so for me, this is not a philosophical. This is not a theoretical idea here. All right. So last time, just to review, we talked about the halo situation with the halo person standing on this thing that's spinning around, and how the normal force of that platform can hold a person up, and the normal force and the acceleration in the same direction. And so what I did was I showed you the wrong way to analyze this thing, which happens to give you the right answer, which is like this, which you say, okay, well, there's a normal force, but then there's some kind of like centrifugal force pointing in the opposite direction, and the two balance each other out, and you can solve for n, and lo and behold, you get the correct answer. If this is Webasine, you would get the correct answer. But the problem with this is that it implies that the object is not actually accelerating, even though it is. It's accelerating because it's moving in a circle. Like this whole thing is spinning around. And so that's not quite right, and if there was any other force you had to add to this, you could very easily get this question wrong. Any kind of variant to this question you can probably get wrong. The correct way to answer this question is to say, well, I have a thing that is, the only force that's on this person is the normal force. So when I sum up all the forces that are in the radial direction, the only force that comes up is the normal force. The sum of the forces always equals the mass times some sort of acceleration. And so sometimes I put an a sub r here just to say the radial acceleration, something like that. Which is the same thing as like the circular acceleration. So sometimes I have a sub r, sometimes I have a sub c. But in any case, because we are moving in a circle, that acceleration is v squared over r. And so if we wanted to add forces to that, or if we wanted to like jump or something, so there was a little bit more than this, that we could. This is flexible enough to accommodate that. So this is the right way to do it, and this is the wrong way. And again, the difference is because the object really is accelerating. It's on a platform that's spinning around quickly. All right. Now it's the same thing with string tension. So if you remember our little air hockey puck, we had a string attached to it. The analysis is all the same. So the only difference is that now there's a string here, and so we have a capital T for tension here instead of normal force or whatever else we were doing before. It's a little confusing that we use the same symbol for the string tension as we do for the period, but usually those two things are decipherable. But in any case, the math is all the same. The last thing I want to talk about is a centrifuge. So there's a lot of different applications of centrifuges. So in the worksheets, it talks about using a centrifuge to try to make atomic bombs, which we'll talk about in a second. There's other applications for centrifuges, for example, in trying to separate the plasma in blood from the red blood cells. So this is a picture of that. And then in the next slide, I'm going to show you a video of someone who is using a centrifuge to purify honey, and I'll talk about that in just a minute. But the basic idea of it is that when you have a centrifuge and you're spinning something around, so for example, when you have blood in here, your red blood cells are slightly higher density than just the water in your blood, or the plasma. And so if you spin it around like this, it causes the denser things to sink and the lighter things to rise. in a way that happens much more quickly if you just sort of let it sit there. Because effectively this sort of makes it, sort of greatly magnifies gravity in some ways. So that's the basic idea, is that the denser things sink and the lighter things tend to float, is the basic idea, both for the honey thing and also for the atomic bomb thing we're going to talk about with the worksheet. So this is making honey, and if you want to watch the video you can watch it there. So you notice this says 1200 Gs, so the acceleration is 1200 times 9.8 meters per second squared. Centrifuge. The basic idea of this is that they're going to pour honey into the spinning thing, so they're sort of showing it off now. There's a motor on the bottom to make it spin around, and so here's the spigot where the honey's going to come out, and they're going to start spinning this thing around. Now this is an interesting design, because what happens is that you want to separate the crud in the honey from the honey itself, so that you can, because you only want to sell the honey, don't really want to sell the crud, for the most part. So so they pour in the honey, and what happens is that because they're spinning it so fast, it turns out that the crud is denser than the honey itself. And so the crud goes to the outsides of this thing, and the honey sort of floats above it. And if they put enough honey into it, then the honey sort of starts to spill out of the edge of this thing, and sort of kind of slews out and then sort of fall all the way down to the bottom, and then they can catch that purified honey and put it into your little honey container thing. So again, that at the end of the day, all the crud is left in here, whereas the nice purified honey without chunks of wax and whatever else in it ends up in here. So it's kind of an interesting design. Now for the worksheet, which I'll talk about, the worksheet, let me go ahead and bring that up here. The worksheet talks about making atomic bombs. And if you're going to try to make an atomic bomb, you might want to use something very similar to this. And the reason that you're trying to do this is because there are certain isotopes. So for example, there's uranium-238 and there's uranium-235, where 235 is the total number of nucleons in the nucleus, compared to uranium-238, which has 3 extra nucleons. And it turns out if you want to make a bomb, then you only want uranium-238. And fortunately or unfortunately, that there might be only, like in a sample of uranium, there might be only a small amount of it that is the kind of uranium that you can use to make a bomb. And the rest of it is the uranium-238, which is not so useful for making a bomb. And so you are in the situation where there's something that is ever so slightly less dense than the other thing, that you're trying to separate those two things. And so if you spin it around like this, then the uranium-238 will sort of float to the top of this thing. You can extract it, and then the uranium-238 will be, plastered on the walls of it because it's slightly more dense. So I originally wrote this worksheet when I think it was probably 2014, 2015, where Iran's centrifuges were in the news. I don't know that Iran's centrifuges are no longer in the news, but the story in 2014, 2015 is that there was a virus, a computer virus, that very cleverly managed to damage these centrifuges by spinning them too fast. Excuse me. So this was called Stuxnet. It's a real thing it's a real thing that happened that you can Google and learn more about if you're curious. But basically they spun it too fast, and they spun it so fast that it actually damaged the centrifuges. And so the worksheet kind of asks, if a certain amount of force, centrifugal force, is strong enough to like damage the metal here, how fast would you have to spin this thing in order to do that? So not quite exactly what happened in that case, but it's similar enough that I think it might be interesting. So this is what we're going to work on today for the worksheet, and yep. So that's the basic idea.